John Niedzielski with Gannett Fleming. He is the last person who will be making his presentation. John, the floor is yours.
Thank you. I'd like to thank the DFI Testing and Evaluation Committee for the opportunity to give this presentation today. And the automated people mover described in the title of my presentation is referring to the Phoenix SkyTrain at Phoenix Sky Harbor International Airport in Phoenix, Arizona. For my presentation outline today, first I'll talk about the project layout and the phasing, the site geology, talk a little bit about the subsurface investigation, the final design for the Phoenix SkyTrain Stage 2, and the results of a vertical and lateral load test on a drilled shaft for design of Stage 2. So here's the layout of the Phoenix SkyTrain system. In this aerial photo, the blue lines represent elevated guideway. Green lines are at grade and below grade guideway. And the red rectangles are the various stations. The yellow area out to the east is a maintenance and storage facility. So stage one of this project starts from the 44th Street station, which has a connection to the light rail system, extends south and west to Terminal 4. Stage 1A is a portion from Terminal 4 to Terminal 3. Stage 2 is under construction now. This is a little over 2 miles long, and that extends from the Terminal 3 station to the west and ending at the rental car center. So Stage 1 opened in April 2013. It has 9,000 feet of elevated guideway, about 2,000 feet of at-grade guideway. It includes the first transit crossing over an active taxiway. There's a photograph to the right here. This was an opening ceremony when this taxiway was opened back up to air traffic after the bridge was completed. Stage 1 had 3 stations and 227 drilled shafts ranging from 45 feet to 105 feet deep. Stage 1A opened December 2014. It has about 2,000 feet of elevated guideway, about 1,600 feet of at-grade and below-grade guideway. It passes below 2 adjacent north-south taxiways, and there's 1 station at Terminal 3. Stage 2 is under construction now. The design was started in 2017. It has 6,825 feet of elevated guideway, 3,370 feet of at-grade and below-grade guideway. It passes below 2 future north-south taxiways, and there are 2 stations and a future station at a future west terminal. There's 182 drilled shafts for the guideway and stations for Stage 2. So the delivery team for Stage 2 of the Phoenix SkyTrain, the owner is the City of Phoenix Aviation Department. Gannett Fleming is providing planning, facilities design, and construction oversight. We have a number of sub-consultants that we're working with. Liam Elliott is providing the people mover systems procurement and oversight. Pencil Phelps is a construction manager at risk. And Bombardier is a train supplier under a design, build, operate, maintain agreement. So the scope and goals for the Phoenix SkyTrain Stage 2 are to extend out to the rental car center, eliminate all of the rental car center buses, reduce the roadway congestion through the airport, improve the ground transportation operations, and accommodate future expansion, particularly on the west side of the airport. There's plans for future hotel and possible retail development. This is a $745 million program. This includes all the systems costs with 18 new train cars, and it's scheduled for a 2022 opening. Just a couple of views, conceptual views of a couple of the stations. So the 24th Street station. 24th Street station from the ground level. Near the station is plans for future development. This is Rental Car Center station in front of the Rental Car Center. And this is a platform level for the Rental Car Center station. So the site geology at this site, typically there's granular fill, can be a few feet to several feet deep. Below that is native silty sand, sometimes native clay sands and sandy clays. And then below that material is sand gravel cobbles. The B2 and B3 subunits are known locally as SGC. This material contains occasional cobbles in the 1 foot to 2 foot diameter range. And B3 subunit has more fines content than B2. It's also more of a reddish brown in color. Below the SGC is base and fill. These are clay and silty sands with gravel and gravelly clays. These are typically cemented materials. And then below the base and fill lies the bedrock. This can be camel's head formation, granite, gneiss, or schist. Just a couple photos of excavations in these sand gravel column materials. To the left, this is a drilled shaft excavation for stage 1A. This is a abutment foundations, 4.5 foot diameter shaft. You can see the cobbles on top of the auger, and also all the cobbles from the spoils is kind of typical of these materials. The right photograph shows excavation for spread footing. This is for stage 2, an abutment. And it's a 4 foot wide excavator bucket. Again, quite a few cobbles you can see within these materials. So the geotechnical investigation for stage 2, we did 113 borings for the guideway, the retaining walls, and the 3 propulsion buildings. We did rotosonic drilling for all the deeper borings. And for some of the shallower borings, we did, for the retaining walls, we did Odex drilling. This is a type of percussion drilling or hammer drilling. And the elevated and below grade guideway boring depths range from 80 feet to 146 feet below the ground surface. There was no bedrock or basin fill in any of these borings for stage 2. We did encounter these materials for stage 1 in the northeast part of the site and then the southeast part of the site. So we're working on an active airport, and we had some pretty tight squeezes to fit drill rigs in. This is a limited access rotosonic drilling rig, and had to get this drill rig squeezed in between these saguaro cacti without damaging this cacti. So kind of some challenging situations in some cases with getting a drill rig in place. So the stage 2 elevated guideway has 4 abutments and 75 piers. There's additional piers supporting the 2 proposed stations at the 24th Street station and the rental car center station. There's a future station at Future West Terminal. Drill shaft foundations for the piers are 6 feet, 7 feet, and 8 feet in diameter. The diameter of the abutment drilled shafts is 4 feet. Fairly high loading conditions. These are loads per drilled shaft. Most of the piers have 2 drilled shafts, but some of them are supported on 1 drilled shaft. Axial loads up to 3,120 kips. Shear loads are up to 260 kips. And moments were up to 10,600 kips feet. So back in 2008 for stage 1 next to Terminal 4, we did a Osberg cell load test. And these are the net unit side shear values from that load test. Very low values at the top of the shaft and not mobilizing skin friction. Also, we did have an issue with some loose soil inadvertently placed up against a temporary casing for this shaft. But when you get down near the O-cell, very high net unit side shears, about 14.5 KSF and 17.9 KSF. And these values compared to the AASHTO 2002 beta method, where we'll get about 3.3 KSF skin friction near the O-cell. And if we look at the 1999 FHWA drilled shaft manual, assuming cohesional side GM, we'll get up to about 5.8 KSF side shear near the O-cell. So quite a bit higher side shear values obtained from this load test back in 2008. Now, I did a paper in 2011. I was a co-author on that paper. This is a plot from that paper. This is elevation in meters versus ultimate drilled shaft side resistance in kilonewtons. The curve to the right represents the O-cell test results from stage 1. And here we're comparing several different analysis methods. This is Reese and O'Neill for sand, for gravels, and Reese and O'Neill assuming cohesional side GM. We're also looking at Meyerhoff and Kohawi and a message from Rollins. We're from 2005, assuming greater than 50% gravel. In this Rollins paper, there were several load tests performed, and this paper has load displacement curves that are developed for skin friction and gravelly soil. So this provided the closest match to this load test from stage 1. For stage 2, we want to do a second load test. This load test is located about 2¼ miles west of the, between 2¼ and 2½ miles west of the stage 1 load test. This is on the west side of the airport. Test shaft was 7 feet in diameter, 60 feet long. There were 3 bidirectional load cells placed in the test shaft, providing 2,100 kips in each direction. There were 2 telltales at the, 2 telltales placed within the drilled shaft, strain gauges at 5 different levels with 4 gauges per level, and then also 4 expansion LVDTs placed at the top of the bottom plate of the cell. The load cells were placed 15 feet above the tip of the shaft, and the load test was performed by applied foundation testing for the drilled shaft test shaft contractor. So we want to do a lateral load test on the same test shaft. Here's a plan view showing that setup. We got the test shaft. We added an inclinometer casing. Actually, the position here is not shown correctly. It's near the reference beam. There's a reaction shaft with a lateral test strut in between. And there was a reference beam placed beyond the zone of influence of the test shaft. So the lateral load test instrumentation consisted of a 10,000 psi pressure gauge in line with the hydraulic pump used to measure hydraulic pressure. There's an electronic pressure transducer with a 10,000 psi capacity placed in line with the hydraulic jack. And the pressure gauge interfaced to a data acquisition system. 2 LVDTs were used to monitor lateral movement at the top of the drilled shaft. There were manual inclinometer readings performed using a slope indicator inclinometer system. And AFT had a data acquisition system controlled by a laptop computer to monitor all the instrumentation. Instrumentation readings are logged automatically at 5-second intervals throughout the test. Just a couple of photos. Here's the AFT cells within the reinforcing cage before the cage was cut and placed into the excavation. Here's a view of the reinforcing cage with instrumentation. The blue cabling is coming from the instrumentation. The blue casing is the inclinometer casing. The gray PVC pipes are for drilled shaft integrity testing. Both gamma-gamma logging and cross-sonic logging were performed on this test shaft, as well as all the production drilled shafts for the project. There's a drilling of the test shaft. This occurred in September 2017, and the sand gravel cobbles was situated about 5 feet below the surface. There's the test shaft in the background, reaction shaft in the foreground, and maximum lateral test load is 300 kips. There are pin connections on each end of the strut to allow for free rotation and translation of the test shaft. Reaction shaft is 6 foot diameter, 35 feet deep. There's the axial load test in progress. Water supplied to the load cells up in the foreground. AFT is taking readings on a laptop computer with the instrumentation to the background on the right. There's a setup for the lateral load test. We've got the aluminum reference beam in the foreground. So this is the lateral load test in progress. Jack and pressure gauge off to the left. And the gentleman standing on top of the drill shaft is taking inclinometer readings during the test. And these are the electronic displacement transducers used to measure the lateral displacement at the top of the shaft connected up to the reference beam. So for the axial load test results, we got up to a maximum unidirectional load of 4,047 kips. peak unit side shear resistance is fairly low at the top of the shaft. We're not mobilizing the skin friction there. But near the load cell level, we're getting peak unit side shear resistances of 13.4 KSF above the load cell and about 7.8 KSF just below the load cell. And this compares to AASHTO values of about 3.5 and 3.7 KSF skin friction near the load cell. This is AASHTO 2002. The Stage 2 project was not designed in LFT, it was designed using LFT. This is a plot. The orange line is an average value of the skin friction within the sand gravel cobbles from the load test. This is elevation in feet and allowable drill shaft side resistance. Blue line is calculated from AASHTO, and then the pink line is calculated from FHWA. So quite a bit higher, again, quite a bit higher side resistances from the load test. For the lateral load test, we got up to a maximum applied load of 338 kips. We maxed out the lateral test strut. LVTT movements were fairly low. Average was only 0.036 inches. This is a plot provided by AFT. This is just showing the different load steps. Sorry about that. Throughout the test, blue line and the red line and the black line is the average. These are the inclinometer readings. We up to a maximum lateral movement of about 0.35 inches. This is a plot of the load test results in blue versus L-pile analyses. This is lateral load versus pile head movement. And you can see we got quite a bit less movement from the load test compared to what we would have predicted looking at L-pile. So we did not get enough movement to generate PY curves from this lateral load test. This was the first lateral load test done in these sand gravel cobble soils that we're aware of. We did perform L-pile analyses using the lateral load test results to try to back calculate a K value. K is a constant used to determine the Young's modulus of the soil. That's an input parameter in L-pile. For stage 1 design, we'd use the K value of 275 pounds per cubic inch for the sand gravel cobbles. Sand gravel cobbles has a friction angle of 40 degrees and a unit weight of about 135 pounds per cubic foot. So for stage 2, we did these sensitivity analyses, and we ended up choosing a K of 500 pounds per cubic inch for design. Could have potentially used higher values, but we got less and less benefit going up to higher K values as far as shortening the drilled shaft lengths. We also had some data that we looked at from pressure meter tests performed for preliminary design in the sand gravel cobbles back in 2003 and 2004. Here's a plot from L-pile. This is 8 different loading cases for Pier 72. This is pile head deflection versus pile length. And we were able to change this original 30% plan length for this drilled shaft, for this 8-foot diameter drilled shaft, from 70 feet long to 47 feet long for final design. We had similar reductions with other drilled shafts. Without the load test results, realistically, in final design, this shaft probably would have been in the 55 to 60 foot range, but still several feet of shortened drilled shaft. And this particular pier was the highest loaded shaft in terms of shear and bending moment on the guideway. Here's a photograph of the stat dynamic lateral load test, and we did not look into using this lateral load test type for stage 2 design. The cost was a little bit higher, and we did have to convince the airport that these lateral and vertical load tests would be beneficial. There was a little bit of work involved with trying to convince them that the stat dynamic test would have cost a little bit more money. We were also working in the runway projection zone, the RPZ of the airport, We had planes flying nearby. Trying to run this test in that area may have been an issue with aircraft flying nearby. With this test, you kind of get a big bang and a puff of smoke. So I'm not sure if the airport would have allowed us to do that in this area, but certainly we would consider this in the future and these for lateral load tests in these sand gravel cobble materials. So we're able to shorten all the elevated guideway drill shafts for the project, typically in the 5 to 10 foot range, typically more close to 10 feet. The cost savings for the guideway drilled shafts is estimated to be $3 million. This is less the cost of the load test. And this was the largest VE cost savings of the project. There was value engineering done before construction, and this happened to be the largest cost savings. Load test costs for the combined lateral and vertical load test was approximately $286,000. Drilled shafts were started in April of 2018, and they were completed successfully by Case Foundation in mid-September of 2019 with really no issues. So our conclusions are that the load test provides a direct measure of performance using the construction means and methods planned for the project and the site-specific soil conditions. AASHTO and FHWA design methods are conservative for design of drilled shafts in these site sand, gravel, and cobble soils. We saw this previously from this load test performed back in 2008. So we expected that again for stage 2. Without any load tests, we would end up with obviously more costs, deeper drilled shafts with additional drilling time, potential issues with caving soil conditions. These sand gravel cobble soils tend to cave quite a bit. If you want to excavate for say a 5 foot diameter shaft, you need to use something like a 3.5 to 4 foot diameter auger due to all the caving. Would have had longer temporary casings without load tests, and would have had to use longer and heavier reinforcing bar cages, possibly resulting in larger crane sizes for the drill shaft contractor placing the rebar cages. That's all I have. Thank you.